Hey everybody, today we're going to talk about the combined gas law, and you just get me. Mr. Bergman is not here to make this for me right now. This will be short and sweet and to the point. Now, the reason we call this the combined gas law is because it combines all of the other gas laws that we've had. So we've got P1 V1 equals P2 V2. Okay, we've used that before. How about P1 over T1 equals P2 over T2? Okay. V1 over T1 equals V2 over T2. That should look familiar. There's one that we haven't talked about, and it has to do with N, N1 equals P2 over N2. Okay, N is just number of moles, and this makes sense. If we increase the number of moles of something, we increase the pressure in that same container. So what we're going to do is we're going to combine these. So let's look at everything that's in the numerator. Everything in the numerator is the P and the V. Okay, we notice P's here and V's here, always the numerator. So let's put those in the numerator. P1 V1 over something equals P2 V2 over something. Well, what's it over? Everything in the denominator. Temperature is the denominator, and moles are in the denominator. T1 and 1. T2 and 2. This is the combined gas law. So all the gas laws are combined. The three ones that we learned, as well as something that includes the N for the moles. Okay. Now the nice thing about combined gas law is if you don't remember any of the other gas laws, but you remember this one, you can get the other gas laws from this. So if you want Boyle's law, you just deal with the P and the V, and you ignore the N and the T. Okay. If you want any of the other ones, volume and temperature, you just deal with those. Just pressure and temperature, you just look at those and you just ignore everything else in the equation. So you only deal with the things that actually change. Now if everything changes, you plug everything in. You do combined problem. If only one thing or two things change, you plug in the two that change and you ignore everything else. Alright, so let's do a few example problems with this. Alright, so first we have a 2.3 liter balloon. It's taken from Woodland Park at some conditions, and it's brought to the top of Pikes Peak at some different conditions. All right, so let's go through and identify what we know and what we're going to look for. Alrighty, so here we have a 2.3 liter balloon. That's a volume. That's a V1. 2.30 liters. Woodland Park, 15 degrees Celsius. So that's the temperature, T1. 15 degrees C. And then that's the pressure here. P1 is 570 millimeters of mercury. Okay, we have a new condition at the top of Pikes Peak. We have a T2, which is negative 15 degrees Celsius. We have a new pressure, P2, which is 425 millimeters of mercury. How big is the balloon? Big, that implies size or a volume, so that's our V2. That's our unknown. Notice that moles are not referenced in this problem, so we simply ignore the moles. So the equation that we'll be using is P1 V1 over T1 equals P2 V2 over T2. We're going to ignore the moles because moles do not change. They're not mentioned in this problem. Okay, so let's just plug our numbers in. We're going to have to do something first. We have to add 273 to our temp to get Kelvin, because we always use Kelvin. Always Kelvin. So 273 plus 15 gives us 288 for our initial temperature, and then 258 for our final. So let's plug these values into our equation. P1, 570 millimeters mercury. V1, 2.30 liters. T1, 288 Kelvin. P2, 425 millimeters mercury. V2 we don't know, so that's what we're going to solve for, over 258 Kelvin. Now, many ways we can go about solving this problem. I think the easiest way is to cross multiply and then solve for V2. But if you have another way that you would like to use, go for it. Now, when we cross multiply, there's kind of a trick that I'll show you here. We're going to multiply these things together, okay, and then we're going to divide the other two. So the ones that are with the variable, we divide. The ones that are not with the variable, we multiply. Okay, so again, multiply everything in red here because there's no variable with the 572.3 or 258, and then we'll divide 288 and 425. Okay, so 570 times 2.3 times 258 divided by 288 divided by 425 will give us our V2. And V2 is then 2.76 liters. Plug and chug. That's all you have to do. Let's do another one. Sealed metal container. Okay, that's important. We have some conditions, a volume, pressure, and a temperature placed in a furnace at a new temperature. What will be the final pressure? Let's take a look at what we have and what we need to find. So we have a sealed metal container, with a volume of 250.0 milliliters. We have a pressure, 1 atmosphere, and we have a temperature, 25 degrees Celsius. Okay, placed in a furnace that is at 500 degrees Celsius. So there's T2, 500 degrees Celsius. What will be the final pressure? Okay, we're solving for P2. Question mark. Now wait, what about my volume? What's my V2? It didn't give that to me. And I'm looking for P2, so I can't look for two variables. Oh, it's a sealed metal container. Metal containers don't change volume, so the volume didn't change. Think of like an aerosol can. You throw that in the fire, the volume's not going to change. Now, it's probably not a good idea to throw it in the fire, okay, because it'll explode in your head. So the volume is 250 milliliters, both times, V1 and V2. So again, P1 V1 over T1 equals P2 V2 over T2. No mention of moles, so we're not going to do that. Now, the volume is the same, 250 milliliters on both sides. We can ignore volume because it did not change. So we're left with P1 over T1 equals P2 over T2, gas law that we've used before. So let's plug the numbers in. P1, 1 atmosphere, over T1. Oh, can't use 25, have to add 273. So that's 298 Kelvin. Okay, 25 plus 273 is 298. Okay, P2, don't know, that's what we're looking for. Can't use 500, we have to add 273, so that's 773 Kelvin. Cross multiply and solve for P. P2 equals 1 times 773 divided by 298 equals 2.59 ATMs, atmospheres. So again, this one we're using the ideal. It started with the ideal gas, we started with the combined gas law, but it turned into one of our other gas laws because we just ignore volume because it doesn't change. It stays the same. Anything that stays the same or is not mentioned, we don't include. All right, that's it. That's simple. Figure out what you know. Figure out what you're looking for. Plug and chug. Put it in. Do your math. Don't put it in your calculator incorrectly. Bye. See you in class.